Our exceptional speaker of this evening was formerly an early engineer at Couchbase and is currently the co-founder and chief architect of Imanis Data. Please welcome Srinivas Vadlamani.
Thanks for the introduction. Thanks for everyone for this talk here. All right. So the bulk of my talk is going to be about backups and recovery in the context of big data. Right. And so I'm going to start off with a few real-world examples of where people have lost data. So what we did last year was we did a survey and asked people to tell us how they may have lost it at some point in their organization. And then it could have been as part of a user error, or they probably just didn't have the adequate backup mechanisms. And so I'm going to talk about 3 of those that I found were amusing in some sense. And then the lessons learned and the business impacts of losing your data. And then the second part of the talk is going to focus on if you have to build an architecture for a big data backup or recovery solution, like we have built in our product, what are the founding principles going to be, right? And then, especially in the context of NoSQL databases such as Couchbase, Mongo, or Hadoop. So the first example I'm going to talk about is, so this was, a big online platform for developers. They had a big production database, and that DB1 is actually how they named the database, which is unreal, but that's not. They had a standby database called DB2, and what they were doing was essentially they had a bunch of different, what they thought of was as the backup mechanisms. They were taking snapshots. These were NFS level snapshots. They had backups going to S3. They were also taking database dumps periodically. And they, of course, had this replication from DB1 to DB2. What happened one day was they got a ton of requests. Spammers wanted to just mess around with the database. And what that led to was the destruction database went down. Obviously, the replication stopped. And then, accidentally the DBA wanted to delete some files on the standby database, thinking, maybe that would make it come up. But then he actually ended up deleting the files on the production database. So overall, the problem was that replication was not working. They had these snapshots going back to a day, and they tried to piece together data from multiple sources, but then they still ended up with about 6 hours of data that was lost. Right? A lot of downtime, which is really bad for business. Turns out that even though they were taking these database dumps and putting them on S3, no one bothered to really check whether they were actually working. So they never did this. Once in a while, you try to bring them up and then make sure that they're working, so they won't get that. So, moral of the story is there's a lot of bad stuff that happened here. The second incident, this was a big Hadoop cluster. You can see petabytes of data. And their idea of protection was just the default replication that comes with Hadoop. So you have 3 replicas in most cases. And they were thinking of that as their backup mechanism. Again, this was a mistake by one of the DBAs, I guess, or a developer. They accidentally dropped a huge table. Right? And with replication, if you have good things going on, they get propagated. If you have bad things going on, they get propagated as well. Right? So this table got dropped from all the replicas, and that table had 500 terabytes of data. So they didn't obviously have the backups. So now they had to rebuild the data from their original data sources. And that took 2 weeks. And then more than $1 million lost. And this third example is some people have, what's called a secure storage. So essentially what they do is they have storage that is managing deletion of data. So if you try to do something something like the equivalent of an RID or a delete file that will not work. So in this particular case, this was a CRM application. And so they had these contracts from their users that they were storing in the database. The CRM application would configure what the retention should be, but then the storage itself would be responsible for deleting the data at the appropriate time. So what ended up happening here was one of the sales rep accidentally changed the retention for a huge customer that they had, a bunch of contracts visible to it. And then that caused the storage to go ahead and delete all of the data. Now again, they were not using backups in this case. They just were thinking of the secure storage as a way to protect accidental data deletions, but there's still no backups. And so they lost all of the data when this thing happened. And so again, this led to a lot of problems in the organization. The point of all these examples was to emphasize some misconceptions about backups and recovery when it comes to big data. And so here are a few lessons learned. Some of this might seem very silly, but again, like I said before, this stuff has happened. So bear with me while I go over some of these things. Right? Use distributed databases. We saw someone use DB1, DB2. Right? That doesn't really help when you're under a lot of stress. Some other things. Particularly something to focus on is the third bullet point, which says use multiple replicas to protect yourself from hardware failures, but that's just replication, that's not bad. So it's very important to know that's not bad. And the same argument applies for remote replication. A lot of people do this DR kind of thing, and they expect the data to be there when something goes wrong, but you need not go back in time and do a point-in-time recovery. And obviously, you have to be very thoughtful about what kind of data you're managing, what kind of data is more critical from a backup perspective compared to some other data that maybe you want to have backups, but maybe it's not that critical. So this notion of RPO, RTO is very important to factor in when you're thinking of backups. And obviously, like in the example we saw where they were doing these SQL database dumps, and then moving them to S3, but they never bothered to check whether that was working. Right? So making sure backup processes are working all the time, monitoring them is extremely critical. And very quickly here, we have to preach the choir here, but the impact in terms of the business is, revenue lost, productivity lost, and all the other bad stuff that could happen. Right? So with that as a context, I want to move on to the next part of my talk, and the focus here will be what should the architecture be if you were to design a backup solution from scratch, right? And so in the past, you may have heard of things like net backup, Veritas with its own backup solution. These are all meant for single node databases like Oracle, MySQL Server, and file systems. But in the big data era where you have distributed systems like Cassandra, big Hadoop systems, and so on, those solutions don't really work. Right? So that's where Imanis data comes in. And some of the principles that we built the system on were as follows. First of all, you have to know that the things that you're trying to do these backups for or data management for are huge distributed deployments themselves. Right? So you have to be a scale-out solution yourself. And so what that means is, let's say you have a 100-node Hadoop cluster, and then over the next couple of years, it's going to become, let's say, 200 nodes in size. So the backup solution that you're using must also be able to scale proportionately. You shouldn't have to buy a new appliance to replace the existing backup solution. So that's the scale-out part. The second part is the data transfers. Right? There are many nodes available on these primary data platforms, and there are an equal number of nodes, in some cases available on the backup platform as well. So when you do these data transfers, whether they be for backup or for recovery, the transfers must happen in a completely parallel fashion. Right? So you should try to maximize the network bandwidth that's available to you. Also, it should be an agentless model. What this means is, used to be that the previous systems required you to install these agents on the system that you're backing up. And so, if you're backing up a file system, you would be running something there that would periodically send updates to the server, and same with the database. But if you have a 100 node cluster, right, install agents on all of them and making sure they're up to date, or that if a node goes down, how do you make sure that that agent will work well? So that whole problem becomes a nightmare. It's a very hard problem to solve. So instead, the way to go would be an agent-based model where instead of these agents running on the clusters, you would connect to them using native APIs. So if it's Cassandra, you would connect to them using file system APIs to pull in the access tables. If it is Hive, then you'll be able to connect to the Hive Metastore APIs. And for the file part of a Hadoop or Hive system, you'll be able to use WebAssembly if you're familiar with that stuff. So using these native APIs is extremely important because then you don't have to install agents on the clusters, and that creates a huge operational nightmare. The second aspect of big data is, of course, its volume and variety. Right? With so much data, you have to make sure that the data you're backing up is sufficiently compressed and also deduplicated. Oftentimes, it happens that the same data gets repeated or duplicated multiple times from where it's getting backed up. Right? Oftentimes, there are also multiple replicas of the data that you're backing up. So it's extremely important that once the data is backed up on whichever system you're backing up to, then you run these specialized deduplication algorithms. You may have heard of a company called Data Domain. They used to do this very low-level, byte-level deduplication. So what we have done in our case is we have re-implemented something like that, but at a scale-out level, which means that our metadata is strewn across all the different nodes, and the algorithm runs also in a completely parallel fashion. So when you're deduplicating something, it could be across your Cassandra or your Hadoop databases, or it could be across some other file system that you're backing up. But we'll be able to identify duplicates across each of these, and then keep a unique reference to the blocks that are unique, and then everything else is just a reference. That way, you achieve a lot of storage optimization. And on top of this, we do this implementation. So if you're aware of Cassandra, the SSLs are already compressed. In Couchbase as well, they're compressed. But then once you bring that data onto a secondary cluster like Imanis, you can do more aggressive compression. And so overall, the idea here is to achieve a very small storage footprint for the data that you're managing already. The second aspect of that is it's very common to have, if you're dealing with Hadoop, it's very common to have millions of files. And same with other NoSQL databases like Cassandra. And so if you want to do a recovery at some point, right, you don't have to recover the entire thing. You should be able to quickly search for things that you're interested in. Let's say a small, directly within a huge file system is what you're interested in, or maybe even a single file that you want to recover. So you need some kind of a metastore or a catalog that's running on the secondary system, which could index all the data that's being backed up, and later when you want to do a recovery, you just do a quick search on the system. And I'll show you a demo later on. We have a Google-style search interface for the data that's being backed up. So you can just search for an object, and it'll come back saying, okay, I need this one or two instances of this object, and it'll be backed up on the system. And within that object, you can do a kind of a time travel, where you can say, okay, show me the first time this object was created and all the subsequent mutations or modifications that were made to that. And you can pick a specific point in time that you want to recover. So that makes it very easy. So having a catalog is extremely important. Otherwise, you might just have a ton of restore points, but you really don't know which one you're interested in, which restore point a certain object will be found. It just becomes very hard. The third point is extremely important. At big data scales, you're moving terabytes, sometimes petabytes of data. So if you're doing backups, you cannot be doing full backups every single time. Right? So you have to start with a full backup. Of course, the first time that you are pointing to some data, but then there onwards, it should always be incremental, truly incremental. So if I have, let's say, a file system with a million files in it, and then at any time 1,000 of them get mutated, then the first time I look at this file system, I will back up all of the files. But then onwards, only the files that got modified, I should be able to just back that speeds up the backups, improves your RTO, and then make sure that the backups are finishing at timely manner. And lastly, fast and granular recovery. I spoke about the granular part, where given a file system, you can drill down to a specific file that you want to recover. And then in our system, this extends to different kinds of data platforms in a data-aware manner. What that means is if you're backing up a file system, will let you search by a directory or a file. If you're backing up a data warehouse, you can search by a database, a schema, or even a partition. In case of Cassandra, it would be like key spaces or column families. In case of Couchbase, it would be buckets and documents. And briefly spoke about this as well. It's extremely important that you be application aware. What that means is that if you're backing up a Hadoop file system, then obviously you're just interested in the files. If you're backing up, let's say, a Hive database, you're interested in both the files as well as the metadata that goes with them. Right? So you might be storing the metadata in a MySQL database or Postgres, whatever. But then the backup system should be able to capture both the metadata and the data together in a consistent way. And the story optimizations that take place on the secondary system, such as Imanis, must also be content aware, because obviously the data that's coming in is different for each data platform. And so if you want to do advanced optimizations like deduplication and compression, you should know what the formats are. So that in some cases you can decompress, do the deduplication, and decompress using a more aggressive compression. So at this point, let's look at what a typical deployment looks like. At the center, you have the Imanis data cluster. So just like the data platforms that we're managing, we ourselves are a distributed cluster, right? So you typically start with a small 3-node cluster, install our software on it, and this cluster lives alongside your other clusters. And this whole deployment could be either on-prem or on the cloud, right? You're completely agnostic. And the thing to remember here is that once you install us in this manner, then you could point us to any of these data platforms. You may have one or more of these in your organization. And a single cluster running Imanis would be able to manage all these different data types. Right? So it's a single pane of glass through which you can accomplish all your data management functions. Let me know if you have any questions along the way, or we can move it. In addition to all the different ones that you see on the left-hand side, we also have support for the different kinds of cloud environments. And so, underneath our, in our software stack, we actually have taken Apache Hadoop and then modified it heavily, especially the data node and the name node components of it, to have native cloud integration. What that means is, let's say you're backing up some data, and so the data arrives on the Imanis cluster, and then you've set a policy where you say, keep the data on Imanis for, let's say, 15 days. And then after that, move it to my S3 account. And so there will be some processes running on Imanis which will back up the data, and then as it ages, they will be moved to S3. At a later point, you may want to do a recovery of this data. Now, some of these objects at that time might be coming from the Imanis cluster, but the others would have to come from S3, right? So there are these native integrations within the software stack at the file system level, where for each block of data, we track whether it's on Imanis or on the cloud. And so from the user's perspective, when they search for something and say, I want to recover this, it's a completely a seamless operation. They don't really care whether it's coming from the cluster itself or whether it's coming from the cloud. So it's that kind of native integration that we have with the different cloud integrators like S3, Azure, Integration. And then we also have these, you can also work with NAS and SAN. So the storage on Imanis, by default it's direct storage, but you can also configure a NAS or a SAN device, and it will function just as well on You also see a QA cluster there at the top. The reason it exists there is, so far I've been talking about backup, but another very useful use case that we support is called test data management. As many of you know already, test data management involves taking a copy of your production data and then making a copy of that on a smaller test or dev cluster. And the reason for doing that is maybe you need a slice of the production data for some, if you're a research scientist, you might want to run some algorithms to test on the data so you have real data to play with. Or if you're a QA person, then maybe you want to run some tests on it. But often what happens is the production data has critical PIIs, such as credit card numbers, social security numbers, and so on. Right? So usually what is desirable is that this data that's being copied be also scrubbed for PII, and that you want to obfuscate the critical information that's present in there. So we're able to do all of those things. We call it masking. So if you have all these fields, then you can identify them and then scrub them so that you replace them with fake values. But this replacement is strictly consistent. What that means is, let's say you have a credit card number, and then when you see that, you generate a fake number in its place. But every time you see the same credit card number, whether it's in the same table, whether it comes from a different database, or it may even come from Cassandra or Hadoop, it will always be replaced by the same fake number. Right? So the statistical properties that are on the input side are preserved on the output as well, which is very desirable if you are a data scientist. So we do consistent masking. Another function that's very useful is data sampling. So often this QA cluster might be very small in size. So if you have let's say a terabyte of data on your production cluster, maybe you just need 100 gigs of that. So we can do uniform random sampling of your data and then just pick a slice of that and then come to the destination. People also use something called data filtering. So whereas sampling was completely uniform, uniform random, so you just pick something random and then just copy to the destination. Filtering lets you control using attributes that are present in your table, for example. Right? So you may say, give me all the data from the Northeast region, and then you just copy that to the destination. So a combination of masking, sampling, and filtering is what's called test data management, and that's another use case that we support in addition to backup. So kind of summarize here. So on the left side, you will see all the different apps that we support. Spoke about backup recovery, test data management. Mirroring is just a shortcut. You can think of mirroring as test data management from a source to a destination. Right? Test data management in general will be more complicated, elaborate, where you copy data from a source to multiple destinations. Archival is another use case that we support for some data types, specifically Hadoop. What happens in Hadoop is you start out with multiple replicas for each file, but then over time, as data ages, you really don't want to keep all the replicas around, but you still want to have access to that data just in case you need it. So what we can do in that case is we will monitor the data as it ages, and we can create a policy that says if it goes beyond, let's say, a month, start reducing its replica count. So when you start with 3, then you go down to 2, then to 1, and when it becomes 0, we make a copy of that on our cluster, and then you can eventually move it to the cloud. Right? So over time, you basically try to reduce the storage footprint of that data on your primary cluster. But you still not lost the data, because anytime you want to do a recovery, you can either do the recovery from the Imanis cluster or from the and then the second part is the fact that it's designed for the modern data centers. I spoke about this. We're completely agnostic to where we're running. You can run this on the cloud, on-prem, or on a hybrid cloud. It really doesn't matter to us. And the third aspect is we have deep integration in terms of machine learning as well. As I said before, we're running a modified Hadoop system underneath. And so with Hadoop, you get things like Spark, MLlib, and such. And so what we have done, one of the things that we have recently added is this ability to detect ransomware or even other kinds of anomalous behaviors on the data. So remember, as we're backing up, not only are we pulling the data, but we're also backing up a lot of metadata around the data. So things like how much time did it take to move this piece of data, how much data did we move, how many objects were created or modified or deleted in a given round of that. And as we collect this data, over time we have enough data to actually train a model and then create these predictive models that know for your particular use case what the right behavior or statistic behavior is. And anytime we see a run that violates that pattern, then we flag it as, it's possibly a security threat, or it could be, some other kind of anomalous updates. Like let's say, one of our customers periodically goes through and updates their entire database, right? So the first time we see something like that, we think, oh, something is wrong here. But as we see that repeatedly, and we look at a month or so, then we learn that behavior as well. So we will adapt to that and say, okay, this is part of the steady state behavior of the system. So we have this kind of capability. On top of this, the user can also provide us feedback. So when we flag some data point as this looks like an anomaly, the user can say this is not an anomaly. For data point that we say everything looks normal here, they can say this is something went wrong here. So we try to learn from that behavior as well. So there's user feedback in that environment. The other thing we're working on right now is the third part, which we call predictive recovery time details. So the biggest thing here is traditionally it's been a really hard problem to determine what the right backup frequency should be, because a lot of stuff is happening on your production cluster, and you really don't know how frequently or at what time you should run a backup so that your business recovery point objectives are met. So there again, you can use interesting machine learning algorithms, specifically rainforests and such, where you try to model the system using a bunch of different variables. You collect a lot of the data, train your model, and then once you have that model, then it can tell you what's the right time to run a backup check, so that your target recovery objectives are met. Kind of spoke about this, so let's skip the slide. So basically, what it's trying to say is, underneath we're running Hadoop. We took Apache Hadoop and then modified it heavily, and then we implemented a software-defined storage engine. It just means that you can take commodity hardware and then install this on top of it, and then we'll be able to give you all that functionality. And then we also added capabilities. So since we have a lot of this libraries that we And then here's a quick case study. There are others too, but I just focus on this one in the interest of time. So this is a big customer that is running Cassandra in the cloud, right? EC2. So what they do, they have 52 nodes and 58 terabytes. It's a pretty big installation. They're using the Imanis data right there in the center to back up this database, but also to send the data across to a remote data center. So with this one workflow that you create in Imanis data, you can achieve both backup and recovery at the same time. Sorry, both backup and PR at the same time. And then you can also push data out S3 so that data doesn't have to live on Imanis all the time. That reduces the storage requirements for the cluster. So next I'm going to go to the demo. Any questions so far? Otherwise I can jump into the demo right away. So what you're looking at is the management console for the Imanis data cluster. If you think about that deployment picture I showed before, we had Imanis data running in the center, a bunch of other data centers on the left-hand side. So this is a web app running on the Imanis cluster. All of this stuff is running on AWS, by the way. What we've done is there's a few nodes running Imanis, there's a few nodes running Cloud Data, Cassandra, and so on. So I'll quickly show how a backup and a recovery works, and then we'll quickly also go over a masking workflow, and then I'll also show how to run some other stuff. So the way to do that is you just go to the data backup section and then say, start a new data backup workflow. So you have to specify what we call a data repository. A data repository is just one of these primary clusters whose data we're managing. Right, so in this case, let's pick Cassandra for this use case. Right? So when you do that, it goes to the Cassandra cluster and fetches you a list of all the key spaces that are available on that Cassandra cluster. Now you can either select entire key spaces, or you can drill down and pick individual column families. Right? As you make these selections, it adds them to this selected data list. The reality is this Amazon cart, right? Where you can review stuff. If you don't like something, you can delete it. So once you have made this selection in this manner, we have a bunch of policies that I did not go over just in the interest of time. But you can say, I want to back up on the cloud. When you do that, it shows you what it's going to do here, right? By the way, you can see references to Helena. That's because we are still not made the complete plan change in the cloud. So it says here that the data will live on Helena for a day, and then it will be moved to the cloud where it will stay for 365 days, right? And then it will be deleted. So all of this stuff, once you define as a policy, we will take care of making sure the data is properly managed. And here it talks about when the backup will run, so that's the schedule. And then finally, because this is cloud, right, you can specify, I will put it on S3 on Azure. If you say S3, then you have to pick a bucket. Right? So I click a bunch of buckets here, and you pick one randomly. And then we have a bunch of other advanced options where you can say, when you're moving this data, make sure you don't hold more data than a certain value. That's bandwidth throttling. You can also configure how much concurrency you want to have. Like, let's say you want it to finish as soon as possible, then you can set a high concurrency. Or the backup itself is not that critical, then you can reduce the concurrency so that the primary clusters are not affected in terms of performance. We also have email notifications, where you can say after the job is finished, send out an email to a person or a group of persons, and that will be sent based on whether there is success or failure. So let's say you've been running these backups in this manner for a while, right? And you can just give it a name here, that's called the job type. And the way it's used is you can use that for monitoring the job later in the system, and you can also use it for doing recoveries, as I showed you. So once you submit this job, let's say I give it a name, and then I submit the job, there's a schedule running in the system that you pick it up, and then based on the policy, we'll run it. If it fails, it will run again. Also, we will collect a lot of logs and stats, and we show all of this stuff in the dashboard so that you can do the first level of diagnosis if things go. Now, let's say you've been running this job in this manner for a few months or so, and then suddenly there's a requirement to do some kind of recovery. So I'm just going to cancel the job here and not submit it. So the way to do recovery is you go to the recovery page, and then you say go recovery. So it again asks you where the data originally came from. So this is just like how the backend workflow started out. So you say the data was on a production Samba cluster, and so here we give you the search interface. So the reason is, again, this is trying to do a recovery, possibly you're under stress. And so instead of having to make you go to deep hierarchies of file systems and other objects, we like to search for things, which is very easy, right? So you can search for different kinds of things, and this is data aware. So because we're doing the recovery for Cassandra, it's showing you key spaces and tables. If this were a file system, it would show you directories and files, right? So on for other data types. So in this case, let's say I know that among all my column families and all the key spaces, there's an orders column family that I'm interested in that I want to recover. So I just specify that here and do a search. In this case, it says I know one instance where this was backed up, and the reason it knows this is because I talked about the catalog before. As we're doing these backups, we index the data on the different attributes, and then store these indexes in the catalog. And so when the GUI searches happen, they go against the database, and that's why the results come back so fast, because we're just searching the metadata, not the data. So in this case, by default, it shows you the latest copy, right? Because that's going to be the most common use case. But you can also pick an older copy, right? And so in this case, we'll show you a timeline of when the object was first created, and then all the different mutations it went through to the latest copy. So if I'm interested in an older copy, I can click that and then say modify the copy. When you do this, it again adds it to the discussion for selected data tab, right? And then so you can now go back and repeat your searches and continue building this list. Once you have all the objects that you want to recover, you go down and then you specify a bunch of recovery options. So either you can put it back to the same location it came from, the original location, or you can put it in a different location. Right? And this different location could be a different Cassandra cluster, where it could be smaller in size, it could be bigger in size, you could have a different topology, it doesn't matter. If you have ever used these native tools that come from these vendors, they have strict constraints about where the data could be recovered. It has to be the same cluster size, same topology, and so on. But we don't have those limitations, and we've been able to work around them in our stack, essentially. So I can recover this data to a smaller depth cluster, and as part of that, you can say if the objects already exist at the destination, override them. If not, then I can give a suffix here, right? And that way I can have both my original and the recovered objects coexisting at the same time, so that I can look at them and maybe do some comparisons later. And then we also have this, so if you're familiar with Samba, when you're recreating key spaces or column families, you can specify some properties for the objects. And so here we let you specify those properties in a way that's different from what they were at the source. So you're trying to recreate a key space, but perhaps with a different topology or a different application. So we give you a lot of flexibility into how this recovery will happen. So that's about the recovery workflow. Then very quickly, let's look at the masking thing I mentioned. So the way it works is, again, I will start a workflow. I'll pick the Cassandra operation cluster in this case, and let's say I drill down the sales key space, and I pick the customers in the order state column frames that I'm interested in for my work. So in this case, I know that the customers table or column family has some critical PII. Right? So we see that there's a full name, there's an SSN. So I can pick here and then select the social security number mask or the full name mask. What it shows here is an example of how the data will look after the masking happens. But what it's really going to do is, like I mentioned before, for each unique value, it will replace it with a fake value, but do so consistently. So every time you see the same value, whether in the same key space, or the same column family, or a different column family, is going to replace it with the same value. So your statistical properties are maintained. On top of that, we have sampling. So the order table is usually very big because it's holding your fact data. So you can say instead of 100%, just give me 100%. We'll be able to do that. Again, just like in the backup case, you can specify a policy. So in this case, this mirroring will happen in a weekly manner, and then you can specify the destination. And once you do this, at the top it shows you the data flow. The data is going to come from a production cluster onto Tulina, where all this masking sampling stuff will happen, and then it will get pushed out to the data cluster. Right? And then the last thing I want to talk about is this ransomware stuff that I showed. So I'm running this stuff in a different instance, so that's why I have to switch to that. So what we did here is we're running a Cassandra backup workflow, and then there's this thing called threat sense. That's our ransomware detection module. It's been turned on. So what that means is anytime the backup runs, it's going to collect all this metadata. It will wait until enough data has been aggregated. The first time that happens is when we generate predictive models. And then from that point onwards, every new backup run will then compare against that to say, let me know whether this new data point looks like an anomaly to you or not. And if it is an anomaly, we flag it as such on the UI, but then we also have a finer differentiation there where we say it's an anomalous update in that someone probably just updated the entire database, or it actually looks like a security threat where, let's say, the file system, the file format itself was changed, as usually happens in ransomware, where they encrypt your files and then you have to provide the ransom in exchange for a key. So now, if you do that, because the files have been encrypted, you don't have the usual file format. Right? So you can use that as an additional point to determine whether something will attack or an anomalous update. So we show you all that stuff here, and these are the different runs of the backup, right from the beginning. And then if you look at this, this was an anomalous update, and we try to flag it using certain algorithms where we say we think it's an anomalous update because an unusually high number of modifications happen very early in the month, and that's not your usual behavior. Right? So using ML algorithms such as random forest lets you kind of isolate things that don't look like their steady-state behavior, and then be able to say something's wrong with that. In another case, you may say, I definitely think this is a security threat because I don't recognize this file format coming from your data source. And then if you disagree as a user with any of these predictions, then you can change that behavior or change that prediction here, and then we will incorporate that feedback in subsequent levels. So over time, as you give it feedback, it will improve. This is very similar to how Google does spam filtering. You can say, oh, this looks like spam to me, but then you can say, oh, this is not spam or this is spam. And it will try to learn from that further as you receive more emails. So that's pretty much everything I had to cover. And we have to take any questions at this point. Yeah.
So with the masking, when you go to a QA database, when the masking goes to a QA database, could you specify? So could we specify our own masks? So
yes, we call it level masking. And so instead of using our mask from the software, you can write your own. And then
what's that using to do that? So
yeah, so we have standard APIs. So you can write in Java, for example. So we'll have a certain set of APIs that you have to conform to. So a very simple example would be you write all your stuff, and then there will be a mask function that we will call and provide you a value as input. And then as output, the contract will be that you will give a mask value, and then we'll use that to send to the destination. Yeah.
Do you guys have any SDKs
For the masking?
SDKs for the API?
So we don't have SDKs. I'm trying to understand like what's the use of this here.
If you want to use another language besides Java.
Oh, for the masking?
Yeah, for the masking.
So rather masking is the only part where you can customize the system right now, because that's the only thing that's usually very specific to a customer's environment. Currently, you can write in Java or any other language that works with JVM, like Scala, or anything of other things. So much of our code is also written in Scala. So Scala and Java incorporate pretty well with JVM. Yeah.
How are you handling security? Are you doing that internally or are you using some that
we're doing it in a couple different ways. When we connect to your data types, we would use SSL, for example. So the stuff on the wire is encrypted. And then data at rest on the cluster is also encrypted because the file system is encrypted.
But for your threat analysis, like what's the algorithm you have?
Oh, for the threat analysis?
Yeah.
Oh, so then I didn't understand your question. Sorry, can you say that
How
again?
you had like part of the visualization was a column indicating the threat
Right.
analysis for a particular backup. Are you like how are you analyzing that? Is that an internal
Oh yeah.
algo?
Right. So the way, I think I tried to describe this before. So we have written an application that uses random forest. If you're familiar with random forest, they are what are called basically decision trees, but a group of them basically, right? And so what you do is you take a model, and you take a bunch of training data, and then you feed parts of the data to each decision tree in the ensemble, right? And so they're all trying to learn some aspects of the data set, but not all of it. And then when it's time to predict something, you ask each of them to say what the prediction is, and then you take a majority vote, right? So we have implemented this thing in our software stack, in Scala and Spark. And so when we're backing up something, we can use that data to do the training, and then later, as we receive new data points from each backup run, we do the predictions. And those predictions are what you see back in the data.
Before we take the next question, I remind everyone we are giving away a $100 Amazon gift card in about 5 minutes from now. In order to be eligible to win this, you do have to be here in 5 minutes from now and put your business card in that bowl or create one out of paper and the colorful paper and pens there. So come up now and put your card in if you have it, and let's take the next question. Yeah, up there.
What would you say like your biggest selling point is, as opposed to like using Amazon or backup property? Like what is the biggest feature and selling point?
Yeah, so for small data sets and where the number of objects are small, where you track them manually, right? It's okay to do these file system snapshots or Amazon snapshots. Just from experience, what we've seen is when you have terabytes of data, or if you have millions of objects, right? It's very hard to track which particular resource point you're interested in, or which particular object you have to do the recovery for, right? So so that's where we come in, and that's one of the important things. The other aspect is when you're doing, let's say, backup of something like Hadoop, right? If you take a snapshot on Amazon, you talk about S3 snapshots or AWS snapshots? Yeah, so AWS snapshots, I mean, you can take a snapshot, but then there's no easy way to do the policies where you say, retain this data for, let's say, 15 days or 30 days, and then after that, put it on S3. So all of that stuff is just not possible for large data sets. And also, running these things on a periodic manner, being able to report on them, and having interesting stacks and logs always exposed. In my experience, that has been the most important thing that our customers look for when they look at the backup solutions.
Up there?
Yeah. On masking, how much overhead does it add? I mean, obviously it depends on what the masking, but if you're reading everything and you're backing it, how much time does it increase on your backup times?
The backup time would be again proportional to how much time it's taking to read, obviously, right? But the important thing to remember is that all of this stuff is happening in a sequential manner, which means that as disks are optimized for sequential I/O, right? So as you are reading or writing, we are doing them inline. So you don't ever do stuff like read stuff, write it back, and read from some other place. It's always strictly sequential. So that gives you a lot of performance, and you only spend time that is needed to actually do the compilation, which is mixing.
Where do you see like a 5% increase in backup time?
It's very hard to say. I mean, it depends on the particular system you have. And also, in some cases, we may do this stuff on the family, like Hive. In other cases, the Cassandra, for example, right? It doesn't support any of this. So we have to pull the data onto here and then. So then that question kind of becomes moot, because we really don't care about what the performance is on the family. Because we already pulled the data. Yeah.
Can you talk about your company? How is it different from Cloudera, Hornwork, and?
Yeah, so it's different in the same way that have you heard of NetBackup or Cement? So these are backup companies for the traditional data. So it's different in the same way that they're different from Oracle or SQL Server and so on. So it has always been that vendors have provided minimal capabilities in terms of APIs or some low-level tools to do the backups, because that's not their focus really. They're more interested in their own roadmaps, and they end up not providing a complete solution. And so companies like us, we can give you not only an end-to-end solution, but also you can use a single cluster to manage across all your data types. Right? Imagine having to do backups on each of your, let's say, 100 couch-based clusters, and then 50 Cassandra clusters, and your Hadoop cluster. So whichever person is doing all of this, it's a big problem for them.
How long have your company been in business? And
We started in late 2012, so we've been around since then.
And over there.
Do you plan to have MariaDB as well?
Sorry?
Do you plan to include MariaDB as well?
MariaDB.
We are mostly driven by what the customers ask for. I've not heard that much about MariaDB backups. Do you guys use MariaDB?
I'm just curious because I don't see your company.
Yeah. We've not come across people demanding a MariaDB backup, to be honest. Yeah.
I have two questions. One is, How do you guarantee consistency in any of these backups? Or you're just relying on the native snapshot mechanism for that?
Yeah, so it depends again on the data type. So for Cassandra, if you know, they have this file system snapshots, right? So before we copy the data over, we take a file system snapshot on each of the nodes, and then we copy the data across. For something like Vertica, we have a proprietary method of doing it. Vertica is, again, everything about is closed source, right? So what we do is, if you're familiar with Vertica, it has this notion of epoch values for each tuple that's stored in the database. So we have come up with an interesting way to look at those epoch numbers and then say, oh, this is a consistent point in time, right? So we do stuff like that for each.
And the other question is about restoring. Why are you especially good? How are you especially good at restoring this data? Since you seem to stress that as an important distinguishing factor.
Sorry.
Restoring the data should be easy. I mean, some people think what you should call a backup system, you should call it a restore system. And concentrate on how easy it is to restore the data.
Yeah.
So why are you especially good at restoring data?
Why are we good at restoring data? So a couple of different things, right? One, I talked about the catalog. Having a catalog lets you search for things very easily. If you do not have a catalog, how do you search? How do you do a restore of? Like, I've seen people that store these file system snapshots. They may have, let's say, 50 or 60 of them over the last couple months. But then when something bad happens, they really don't know which one to pick, right? Because that's usually encoded in some XML files, or sometimes it's not even there because they're using file system snapshots. So that's a big problem. The second part is many of these backup tools that come from the vendors are not optimized for performance. For example, Couchbase's recovery tool can only run on one node, and it can create, I think, like 4 or 8 threads, but they're all running on that one node, and then it's pushing the data out to the destination Couchbase cluster. Now, what that means is, even though the destination Couchbase cluster is kind of parallelized in the ingest, the data reading part is still happening from a single node, so that becomes the choke point, right? In our case, because we have a distributed file system on the cluster, the data is strewn across or sharded to begin with. So when the recovery runs, you can control, let's say, run 6 threads at a time, and then all these guys will be reading data from the respective disks, right? So aggregate disk bandwidth goes up very high, and then you can increase the performance of the restore because of that.
I didn't understand how the presence of the catalog makes it easier to decide what to restore.
So an example again would be, you search for some object and you look at the timeline. And each timeline says, this was a point where it was modified, or this was a point where it was first created. Along with that, it will also show you additional properties of the snapshot of that point in time. We're also adding a new feature where you can compare different revisions or points in time and say, and has the system to tell you what's different about these 2 snapshots. And you might say, oh, in this particular case, someone added, extra 20 rows. Or in some other case, it may say someone changed the owner attribute of this object, right? So having that semantic information being shown to you as a user is very helpful, because you don't have that context, because you never think, I'm going to end up in this situation today. Yeah. So this.
Can you, like, 1 or 2 slides before? No. I think on the demo side, you had the. Further up, like almost the last one that he had. He had the basically the speed of.
This parting?
Yeah, he had like the table.
Yes.
No, there wasn't data kind of like.
Oh, yes. Yes.
Right. Yeah. So my question is this: if you will look at this data, I mean, what technologies are you using underneath that to do the backup? Because it looks like pretty horrible data. I mean, 5 gigs, obviously 5.3 minutes. If you will go to your, even not a petabyte, but for some kind of like, serious data sets, they will not finish in years, not in hours.
Yes, so this is called a facade, a demo facade. So it's not running on real hardware, so we spawn EC2 instances, and we're running this data. This data is populated to be shown here. We're not running this on a real.
Okay, so this is a fake data.
Yeah, it's fake data.
Okay, all right, that's fine.
And to answer your question, what it will be on a real system, the better way to answer that, rather than give numbers, is that we always saturate the network and the disks.
But how do you parallelize, for example, the backups themselves? I mean, this is a serious operations that.
So, an example would be, let's say, startup, right, which has, let's say, 20 SS tables to be backed up. Then you can spawn, let's say, 5 threads on the Telina cluster, and each of them connects to one node of the Cassandra cluster, and then backs up, and then copies the SS tables in parallel. Right? So that's the part that you saw with regards to the concurrency throttling. As you increase the concurrency, you can run more threads or processes that can fetch this data in parallel. So that's what increases the performance. And because they're all trying to read as fast as they can, you can saturate the network and the disks on your data.
And how do you store that data? I mean, in what formats? I mean, you saw it, files. You store, where are you storing that? You have some file system.
So
how you do that?
Yeah, so the Telina cluster. This thing here talks about NAS, SAN, and direct storage.
But it looks like from this picture, it looks like that you store that data into your system. From NAS and SAN, it goes and stores.
No. So NAS and SAN are examples, but you can have direct pack storage on each of these nodes, and that's where the data is being stored. So we have a distributed file system built on top of this cluster, and then the data is getting to that distributed file system.
So what file system are you using in your system?
It's our file system. We've taken Hadoop and then we modified it heavily to work.
So it's some flavor of HDFS you storing?
Yes.
That is all the time we have for questions right now, but Srinivas is here for one of those questions. He will be available right after we wrap off this $100 Amazon card. So, let's just start with it. Can you mix this up? Can I ask you, look out in your check, pull it out, read it out. Calvin Lynn. When the ones who replace Calvin Lynn, go back in.
Did you put your card there?
Brenda? Brenda what? Brenda? Brenda, okay. Wow, we've never had someone not be here. That was the question one there. You after first. Don McLean? The singer? I'd like to give everyone a great big round of applause. Thank you so much, Srinivas. Srinivas, Vadlamani, for coming, and thank you all for coming. Come up here, ask him all the questions you want.